Alright, so this is our second lecture, and probably the last lecture, on the non-parametric statistics. In the previous lecture we discussed the, well, generally speaking, what are the non-parametric tests, and the bottom line of this discussion was that we use non-parametric tests when we're dealing with several, two or more populations of numerical data when the normality conditions are not satisfied. For example, if you're running a test for two independent samples, in order for us to use the t-test, sample 1 and sample 2 must be normally distributed. So if I test one of the samples and the normality condition is violated, then I can't use the t-test, and in this case I have to use Wilcoxon rank sum test. Also, we discussed that these tests are applicable when your data are ordinal, because so far in our lectures up until last lecture we only looked at the cases when data are either numerical or nominal. Ordinal data, which is another big class of data, and actually it's collected in a lot of practical situations, we didn't discuss any tests for ordinal data. So Wilcoxon rank sum test can also be applied when you're dealing with two populations collected independently and the data are ordinal. And then also in the last lecture we discussed what happens if the samples are matched pairs. So for the matched pairs there are actually two separate tests, and in the last lecture we discussed one of them. It's called Wilcoxon signed rank sum test, and it is used when we check the normality requirement, that is differences of matched pairs between the observations in matched pairs have to be normally distributed, and if they are, then we use our good old friend t-test. But if they're not, if the differences are not normally distributed, then we would have to use Wilcoxon signed rank sum test. And actually that's exactly what we did in the very last problem that we looked at. It was about whether or not converting movies from PG-13 to R version by adding explicit scenes to the movie will increase the popularity of the movie. So we took 40 movies, added explicit scenes to each and every one of them, and converted the rating from PG-13 to R, and then we traced number of times each movie was rented. And it turned out that the differences, since we were dealing with matched pairs, each pair was the same movie, just different versions of the same movie. Differences between number of rentals for PG-13 versus R were not normally distributed. So we formulated our hypothesis in terms of locations, not in terms of the mu1 minus mu2, and we used Wilcoxon signed rank sum test for that, right? So today let's start by considering the scenario when again we're dealing with matched pairs. And but this time around, so two populations, matched pairs, but this time around the data are not numerical, they are ordinal. So here is the problem that we're going to discuss. It's kind of fun one. A long-standing question: which is better, Coke or Pepsi? So there are people who believe that Coke tastes better, there are people who believe that Pepsi is better, and there is no way to find middle ground between them. So once and for all, to settle this question, here's what a group of CNU business students, or I don't know, marketing students or psychology students, whoever that might be, decided to perform an experiment. So they found 25 randomly selected PIC students from CNU, and they told them, okay, we're going to give you guys unmarked cups. So the people who performed the test, they knew that they are giving Coke in unmarked cups, but for those who were kind of under the investigation, right, part of this research, of this study, they just, here is here is the drink for you. Okay, we may even have a lid on top of that, right? So that they couldn't pick inside, because you pick inside both Coke and Pepsi, they have this brownish color, right? So if somebody gives me a cup and I look inside and it's brown, I'm like, oh, okay, it's either Coke or Pepsi, so I know. But if I put a lid on top of that, all right, so that they can't even pick inside, then here's a drink, all right? What do you think about that? So and every student who was part of this study, we asked them to provide us a response on a 5-point Likert scale. So Likert scale is typically when somebody asks you to rank something, like for example on a scale from 1 to 5, 1 being the worst, 5 being the best, on a scale of 1 to 7 sometimes it's done, on a scale from 1 to 10, even more detailed research, right? So these different values that we assign to two different ordered categories, that's what's called Likert scale. That's a standard term in this type of subjective research. And when I say subjective, the reason for that is, when I'm asking somebody, what do you think about this drink? How does it taste for you? Right? So it's their subjective opinion. There might be actually people who don't like carbonated drinks at all, right? They prefer to drink either coffee or tea or just simply water, right? There are people who don't drink carbonated drinks at all. So, and that's what's called Likert scale. So they're really different categories, but we assign them different numbers from 1 through 5. So 1 stands for tastes bad, I don't like it. 2 means, well, I'd rather dislike it. It's not very bad, but it just sucks. 3 means neutral, right? I'm okay with that either way, so I don't particularly like it and not particularly dislike it. 4 means, so it's opposite of 2. I'd rather like it. It's not excellent, but it's okay. And 5 means, yeah, tastes good, so I like this drink. So, again, we're giving to 25 students a bunch of unmarked cups, and we know that inside there is Coke, but they don't. And they're kind of giving us the response on the scale from 1 to 5. So after that, we reset. In other words, we give them some water to wash away the taste. Let them sit for about 20 minutes to kind of, let them relax from this first drink. So forget the taste, sort of, right? And then we're giving them another, same people, that's important. We're giving them, again, unmarked cups, no peeking inside, right? But this time around, inside, there is Pepsi. And we're asking them to rate the drink on the same 5-point scale, from 1 to 5 tastes bad to 5 tastes good. And the responses are recorded in the file. So, question is, can we conclude at 5% significance level that people perceive Coke and Pepsi similarly or differently, right? So that's essentially what the dispute is, right? Some people claim that Coke is better, some people claim that Pepsi is better, but how do we find sort of the true answer? Well, this is what statistics offers, right? So let's just collect the data and then decide from that. Okay, cool. So well, let's read the data first. Okay, so I'm going to call it drink data, and that's in the file, in the disk C folder data. I believe it's called Coke _ VS versus _ Pepsi. CSV, if I remember correctly. Yes, that's the case. Alright, so well, let's take a look at how many rows do we have. Should be 25, right, if I remember correctly from the description of drink data. Yes, so there are 25 people, okay, in the experiment. So we performed 25 measurements on the Coke, and then after the 25 measurements on the Pepsi. And so let's take a look at header for the data, drink data. Okay, so here are first few rows, right? So I have 2 columns, right? Column 1, as was discussed in the problem, contains responses of people on the scale from 1 to 5, 1 being the worst, 5 being the best. how did they like unmarked drink, which was really Coke. Okay. Second column contains same people, right? But 20 minutes later, when they forgot the first taste, their responses to Pepsi. Okay, so let me be formal about that. Okay, let's go ahead and go to our analysis flowchart. So in this case, I'm comparing two populations, right? Data type ordinal, right? 1, 2, 3, 4, 5. They're labels. They're not numbers. We assign them to categories, and they are ordered. 2 is better than 1. 3 is better than 2. 5 is better than 4. So ordinal data. Experimental design. What do we have? Matched pairs or independent samples? And the difference is really in how the data are collected, right? So what we have here is we take 25 people, ask them to drink, well, what really is Coke, but they don't know it, and then give the responses. Then same students, right? That's the keyword here. Same students. We give them water to wash away the taste and 20 minutes to forget the taste. And then we give them Pepsi, again, in unmarked cups. So therefore, what really that means is this rating right here, first one in both Coke and Pepsi columns, belongs to the same person, right? So therefore, see, the reason why we're conducting, so this is matched pairs really, okay? The reason why we're conducting the experiment in terms of the matched pairs is I could totally do it as independent samples, right? Take 50 people, split them randomly, group 1, group 2. Group 1 takes Pepsi, group 2 takes Coke, okay? So that's totally doable. But what do I do? What can be another hidden factor that can distort the results of my study? Purely randomly. Okay, I could, for example, get more people who like Pepsi in group number 1. Okay, and I give them Pepsi, so they naturally like it for some weird reason, right? So therefore, they're going to give me higher rankings. Okay, or maybe who knows, right? Male, female. There may be differences. How male population perceives Pepsi and Coke, and how female population perceives Pepsi and Coke. So in my first sample, I can have more females, for example, okay? And let's say females like Coke better. So therefore, naturally, the first population, if I give them Coke, they give more high ratings, but if I give them Pepsi, they give me less high ratings, right? So there are a lot of different things that can mix up in the study if I let the experiments, if I let the samples to be independent. Instead of that, I'm going to say, you know what? Let's ask the same person, right? In this case, I don't care really. So all these other variables that can be part of my, that can distort my results, I really eliminate them, because now male versus female, Pepsi lovers versus Coke lovers versus coffee/tea crowd, doesn't matter anymore, because I'm asking the same person. Here's the Pepsi and here's the Coke. Without knowing that this is Pepsi and this is Coke, what do you think? Which one tastes better to you? Okay, so since I'm comparing same person's reaction to different drinks, that's what makes these observations to be matched pairs. So going back to my analysis flowchart, what do I say? Two populations, data type is ordinal, experimental design matched pairs, and here is the sign test. And that's essentially what my slide here says, previous slide. Okay, sign test is used when I have two populations and the data are ordinal and I have matched pairs experiment. So for by some criterion, the observation 1 in sample 1 and observation 1 in sample 2 are linked together. Observation 2 in sample 1 and observation 2 in sample 2 are linked together. Okay, so something relates the observations on the same line in my samples, right? So in this case, it's the same person's reaction. That's what makes the observations click together, and therefore data set to be matched pairs and not independent samples, right? By the way, if they were independent samples, right, what would happen? So if sample is independent, then I would use my good old friend Wilcoxon rank sum test. Okay, and we did that in the previous lecture. But this time around, I'm going to do the sign test. All right. Well, ladies and gentlemen, for the sign test, we're going to actually use the external library. We did that already, right? Few lectures ago, I believe it was 2 lectures ago, when we discussed multiple linear regression, and specifically the bad condition called multi-collinearity. I showed you in the lectures how we can how easily we can bring the external library, right? Download that, install it on the machine, and use functions included within this external library. I believe we used ggalley library in order to run the function ggpairs. It will calculate the mutual correlations between different columns in my data set, and therefore I was testing for multi-collinearity. Well, here I'm going to again do the same thing and bring the external library to conduct a sign test, because if I start, well, there is sign, but it's not a sign test. There is a function sign, okay, but it doesn't do the sign test. So on your machines, here's what you need to do. You need to install dot, oh, come on, install packages. All right, and the name of the package that we're going to use is all caps, all capital, BSDA. Okay, package is called BSDA. So I already installed that. That's why it's asking me, do you want to restart R? Okay, let's restart R. So it restarts the R for me, and it installs the packages. Okay, start a new session. Oh, that's not a good sign. All right. So, okay. Did I lose it? Yeah, it looks like I lost it, right? Oh no, there it is. Okay, so install the package BSDA, and there you go. Our package is installed, but I have to, because it restarted the session for me. It crashed right in the middle of the installation for me. I'm going to read the data again, because when it restarts the session, it basically loses everything that was in the memory. So I have to read the data again. Okay, so, and again, when you install the packages, you're doing it only once, right? After the package was downloaded and installed on your machine, you don't need to, next time when you perform some sort of analysis, you don't need to install the package again. It's already part of your R environment. And actually it's very easy to see. We never did that before, but for some reason it just kind of occurred to me that here in this window, when you click the tab packages, it will list all packages that are installed on this machine here. Okay, so I have a bunch of them, and you can see that BSDA, which stands for Basic Statistics and Data Analysis, sounds like a good package. Actually, it probably has a lot of functions inside that can do a lot of different things for us, right? It's already installed. And by the way, a couple of lectures ago, when we installed the package ggalley, right, it's still here. All right, so therefore, if right now, for example, I would like to use the package ggalley, I don't have to install it. All I have to do is load the package. Okay, so ggalley is installed right there. So now I have BSDA package, Basic Statistics and Data Analysis, installed. Okay, very good. And remember, the next step, every time when you load install the package, you have to load the package into the active memory, and that is done by the function library. And all I have to do is say which package I want, BSDA, and there you go. Okay, so I load the package. It says loading required package attaching BSDA. The following object is masked from, I don't really know what that means, but yeah, okay, cool. So now I can use the function sign test, which is part of the BSDA package, and it's all caps, I believe. If I start, yeah, so see, I started to type sign test, and there you go, and it even tells me that sign test right there is a part of the BSDA package. So I'm gonna do the sign test, and you can see right here in my little help, right, that shows me how to use this function. It actually follows pretty much the same patterns that we saw before in t-test, in Wilcoxon test. So it's pretty much like once you know how one of these function works, everything else is organized in a very similar way. Okay, so I'm going to do the sign test, but before actually getting, so I think I'm getting ahead of myself here actually. Let's discuss what is that we're testing, right? I mean, it's great that we're ready to rumble, but let's decide what is that we're testing. Okay, so here is the research question, right, that we're investigating. Can we conclude at 5% significance level that there is a difference in how Coke and Pepsi are perceived? So remember how we discussed that 20 or so lectures ago that when you're testing hypothesis, you need to search for the question that is imposed in the problem, and that question becomes the content of your alternative hypothesis. So this is what I'm investigating, okay? So, and because we're dealing with non-parametric tests, right, my test has to be, so essentially what I'm saying is Coke and Pepsi are perceived differently. That's my alternative, right? Therefore, my null becomes Coke and Pepsi are perceived the same, okay? But since this is the ordinal data, and therefore I cannot really use the mean, because 1, 2, 3, 4, 5 are random numbers that I chose to assign to different categories, right? So therefore, calculations of the mean, they don't make much sense, really. So I have to use non-parametric way to formulate my hypothesis, and this is what. So this is Coke versus Pepsi. Okay, so therefore I have to formulate my hypothesis in terms of locations, right? So therefore my null, since I'm testing if Coke and Pepsi are perceived differently, my alternative becomes that the location of population Coke is different from the location of the population Pepsi. So if that's the case, in other words, if the distributions of responses for Coke and for Pepsi are not looking the same, that would indicate for me that there is a difference between them. So therefore null tells me that no, they're not different, they're the same really. Location of population Coke and population Pepsi are the same, so therefore both drinks are perceived people just the same. Okay. Alright, so let's go back to the sign test. Okay, so it doesn't matter really which I put first, so let's put Coke first. So I have drink data Coke, that's my population number 1. Drink data Pepsi, that's my population number 2. And then MD. So instead of mu, difference between the averages, it's difference between the medians. Remember, in the last lecture, we discussed that we can think about non-parametric tests as the tests about the populations, or alternative point of view, it's the test about medians, right? Median 1 is less than the median 2 versus greater versus not the same. So difference in the medians is equal to 0, right? So that's what I'm hypothesizing. There is no difference how Coke and Pepsi are perceived. Okay, and my alternative is two-sided, right? So just like before, not equal means 2 dot sided test. Okay, and that's enough. All right, so I run the test, and here's my p-value. Okay, so p-value is, so you can see that p-value is 0.06. It's barely higher than 0.05, right? 0.06357, but still higher than 5%. All right. So therefore, what does that mean? That means that I failed to reject my null in favor of alternative. Okay. So what does my null say? My null says that the location of population Coke and population Pepsi are the same. So therefore, from this small experiment, when I tried to use same 25 people to taste Coke versus Pepsi and ask them, well, what do you think? Do you like it? Do you not like it? Tell me what's your perception. I didn't find this small test, right? This small study did not find evidence to support the claim that difference exists between Coke and how people perceive Coke versus how they perceive Pepsi. Okay, so this is kind of a scientific point of view, right? So I mean, we can argue all we want, which one is better, right? Coke or Pepsi, Star Wars or Star Trek. Back in '90s, the big deal was who is more cool, Michael Jackson or Prince, right? So we can argue all we want, but this is a more scientific approach. Okay, instead of arguing, instead of being like softy, right? So let's consider different points of view. Why just not collect the data and let data decide who won and who lost? So in this case, we didn't find any. We failed to collect the data that says that there are differences in how people perceive Pepsi or Coke. Okay, so sign test, ladies and gentlemen. All right, and the last test that we're going to consider in this semester, and after that, that's going to be it, is going to be Kruskal-Wallis test. Well, let me tell you that Kruskal-Wallis test is an equivalent of, let me scroll down to Kruskal-Wallis. Yeah, Kruskal-Wallis test right there. Kruskal-Wallis test is equivalent of one-way ANOVA. Okay, I believe when we discussed one-way ANOVA, what was the example that we did? Can't quite. Oh, right. The example that we did was from marketing, right? So the company that makes apple juice came up with a new product, which is apple juice concentrate, but they're not sure how to advertise apple juice concentrate. So they came up with 3 ideas, alternative, right? We can create advertising based on price or convenience or the quality, and let's just air 3 different commercials in 3 different cities, collect the sales data and decide which one will generate, or maybe they're all the same, right? Or not the same. That was our alternative, right? Our null was that 3 different commercials will generate the same amount of sales. And alternative was no, at least 2 will be different, so not all the averages are the same. So Kruskal-Wallis test, so one-way ANOVA applies when you have 3 populations or more, and I told you that one-way ANOVA is like a smoke detector, right? So it will not tell you where the smoke is, but it will tell you that there is a fire. It will not tell you where there is a fire, but it will tell you that there is a smoke, and somewhere there is a fire, right? But not the exact location. So our null hypothesis that we tested for one-way ANOVA was all averages for our k different populations are the same, and alternative was no, at least 2 populations have different averages. And which ones, one-way ANOVA test will not tell you. Okay, we used, I believe, the box plot in order to kind of informally judge which might be different, right? Higher or lower or whatever that might be. Okay, and one of the requirements that we discussed. Let's go back to the same beautiful analysis flowchart. So one-way ANOVA right here, okay, applies when you compare 3 or more populations. Data are numerical. You have independent samples, and every sample is normally distributed. That was the requirement, right, for one-way ANOVA. Well, what if you have independent samples and data, at least one sample is not normal? Then what? Then you're using Kruskal-Wallis. So therefore, Kruskal-Wallis, you can see, applies when we cannot really apply ANOVA. So in other words, when you're testing your samples for normality, and normality is not there. So let's say you collected 3 different samples. Samples 1, 2, and 4 are normal, but sample 3 is not. Then we can't use ANOVA, we have to use Kruskal-Wallis test. So that's one case when Kruskal-Wallis applies. Another case when Kruskal-Wallis applies is when your data are ordinal. Again, samples are independent. Then you use Kruskal-Wallis. So bottom line is Kruskal-Wallis is applied when your data either ordinal or numerical. Samples are independent, and well, if it's ordinal data, then it's just straight up Kruskal-Wallis test. But Kruskal-Wallis applies to the numerical data only when the normality requirement is not met. So at least one or maybe more samples that you have collected fail the normality test. And reminder, we cannot test normality for the ordinal data or nominal data for that matter. Why? Very simple. Normal applies, you can calculate the mean, right? But for ordinal data and for nominal data, so categorical data basically, the calculations of the mean cannot be performed. For a very simple reason, the numbers that we assign to different categories is our choice. They're not objective, they're subjective, okay? Interval data, you measure something, right? And that's it. So you measure people's weights or height or amount of money or temperature outside or the volume. It's not subject to interpretation. It's just a number that is given to you by by the scale, by the by the thermometer or something like that, right? So ordinal data and nominal data, when we assign categories different labels, different numbers, that's subjective assignment. Okay, it's subject to change. So therefore, we can't calculate the mean, we can't calculate standard deviation. Therefore, whole idea of normality is kind of completely abandoned. It's non-existent. Okay, so let's go back and let's take a look at the problem to illustrate, right? But before we do that, let me point out that hypotheses that we test for Kruskal-Wallis test are very similar to the ones that we test in one-way ANOVA. So one-way ANOVA, null is always means equal to each other versus no, at least two are different, right? Well, when we're dealing with non-parametric tests, we replace the word mean with replace location, right? Or alternatively with the word median. So therefore my null is going to be that all k populations, that's general case, right? All k populations have the same locations, or which is the same kind of idea, all k populations have the same medians, right? And alternative, just like in one-way ANOVA, at least two populations locations are different from each other. Okay, so very similarly formulated, but instead of the word mean, mu, I'm using the idea of the population. But that's all the difference really. Okay, so here is an example that we're going to consider for that specific problem. The manager of the fast food 24-hour-a-day restaurant, such as McDonald's, for example, you know that McDonald's work 24/7, right? Most of them anyway. So they have 3 shifts, right? Staffed in 8-hour shifts. So first shift goes from 4 p.m. to midnight. Second shift from midnight to 8 a.m. And the last shift, third shift, from 8 a.m. to 4 p.m. Okay, so this way the location is open 24/7. So the manager would like to compare to see if there are differences between customer ratings. So here's what the manager does. He or she, whoever that might be, collects the data about the service, right? So randomly, for example, from the shift from 4 p.m. till midnight, I'm going to pick randomly, I don't know, 10 customers and ask them, can you tell me on the scale from 1 to 4, 1 being poor, so it's called Likert scale, right? In this case it's 1 to 4. 1 poor, 2 fair, 3 good, and 4 excellent. Can you rate, here you just came in and you had a meal here with us, and what do you think about our food, about the restaurant? Is it clean, is it not clean, just overall, what would you say? So they give me the response, 1, 2, 3, or 4, okay? So the data is ordinal, right? I'm collecting ordinal data. And I'm collecting number of responses for this shift from 4 to midnight, from midnight to 8 in the morning, and from 8 till 4 in the afternoon. Okay, so let's take a look at the data, right? So I'm going to enter a bunch of pound signs here. Alright, so shifts data. .csv. The file is called shifts.csv. Alright, now let's take a look at the header of shifts data. Alright, so here are the three columns, right? I have from 4 p.m. to 12 a.m., from 12 to 8 a.m., and from 8 a.m. to 4 p.m. So, now let's take a look at how many rows do I have. I don't think this file has a lot. So, shift data. Alright, I have only 10 rows, right? So, in each shift, I ask 10 customers to give me the rating from 1 to 4. Okay, so data are ordinal, and I have obviously 3 samples representing 3 populations, right? Customers who come from 4 to 12, from midnight to 8, and from 8 to 4 p.m. Okay, so let's again be formal, and let's use our analysis flowchart. So here, I'm comparing 3 populations, right? 3 different shifts against each other. Data type, ordinal. Experimental designs. Well, I can have independent samples, or, well, the equivalent of independent samples, in case I have more than 2 samples, is called blocks, right? Block of observations. So they're not pairs anymore, right? So what would make my observations to be blocks? Well, for example, it's the same person, right? The same person comes 3 times during 3 different shifts and tells me what they think about the restaurant, okay? So this is a rather special case, right? So likely these 10 customers that came in shift 1, shift 2, and shift 3 are completely different customers, right? There is a really good chance that none of them are the same people, right? So therefore my samples are really independent, okay? They're not blocks. For them to be blocks, that number has to be linked with that number somehow, and to be linked with that number rating, okay? And nothing in my problem indicates that this might be the case. So therefore I'm dealing with independent samples, and therefore there you go, Kruskal-Wallis test, ladies and gentlemen. Okay, so Kruskal-Wallis test, here we go. So how do I formulate the null and alternative hypothesis? Well, let's do that. Okay, so my null becomes locations, let me call them shift 1, shift 2, and shift 3. I don't want to type 4 to 12 p.m., a.m., whatever. Okay, locations of populations shift 1, shift 2, and shift 3 are the same. That means that regardless of when I ask my customers, they give me statistically similarly distributed answers. And in human terms, what that means is my restaurant provides the same level of customer service regardless of time of the day, right? That's really the bottom line of why the manager wants to investigate, you know, if the ratings are the same, right? Because, for example, if it will turn out that shift number 2 gets worse ratings, that means that, you know, for some reason I'm slacking off as a restaurant during shift number 2. Okay, so I have to change something about that shift. But if the ratings will be statistically the same, that means that regardless of the time of the day, we're offering customers consistent service. That's what really the bottom line of it. Okay, so my alternative is going to be that the at least 2, right? At least 2 populations all right, have different locations, all right, or medians, right? So the same test can be formulated in terms of the medians instead of locations. Okay, so this is what I'm testing. Well, Kruskal-Wallis is actually part of my I don't have to download any packages, it's part of my R Studio. Okay, so if I start typing Kruskal test, there it is, performs Kruskal-Wallis rank sum test. Okay, but before we do anything, do you remember how the test was performed in case of ANOVA? I stacked my samples, right? Remember? So what does that mean? Well, that means that right now the way how my data frame shifts data is organized is I have 3 columns right there, okay, and they contain ratings. Technically they're integers, but I know that they're really not integers, they're just labels that correspond to 3 different categories. And the way how we performed ANOVA test, we had to stack all the numbers in one column, one sample on the top of another, and that column was called values, right? And the second column was called ind, I guess it stands for indicator, and that was the column that contained indicators, or indicators really, which sample that number came from, right? So let me show you, remind how it's done, right? So how stacking is done. So stacked shift data. Shifts data is, I have to use the function stack, okay? And it's very straightforward. All I have to do is say stack shifts data, just like that. And when I run this line, the data are stacked. And now if I look at the structure of the data, right? Let's look at the header of the data. Stacked shift data. That's what I'm gonna see, right? Values 4, 3, 3, 2. So we can see that 4, 3, 3, 2, right? So it took my first sample, and I can see that, right, from 4 to 12 a.m. Well, I know that there are 10 of them, right? So I can actually show the entire stacked data set. How? I can go ahead and say n, I believe it's n, yeah, n, show me what if I stack 3 columns, 10 observations each, I have 30 records, right? So let me see the entire data set. Okay, so you can see my first sample is, it ends right here, right? It's from 4 to 12 a.m. My second sample starts from line 11, from 12 to 8 in the morning, and my last sample from 8 to 4 p.m. There it is, okay? So all the data values are in column 1, but stuff that I see in my column number 2 is just an indicator where that number came from. Okay, so now I can actually use the Kruskal-Wallis test, right? So Kruskal test, yeah, Kruskal test right there, okay? And all I have to do basically is, just like I did with ANOVA, by the way, okay? There is not much difference. Remember how I perform, so let me call it Kruskal test, Kruskal test, right? So I'm going to record my results of my test in a variable called Kruskal test. And the way how we did that in ANOVA is we set values as the function of the column index, right, or indicator. So therefore, I'm going to do the same exact thing. Values, all right, tilde, ind is the name of my second column, right, that contains indicators, which column, which sample that value came from, okay? But if I leave it like that, nothing is going to happen. It will say, I don't know what you mean, man. Values, that's weird. I don't know anything by the name of the values, so I have to specify where it comes from, right? So I'm gonna say data, use data, this one right here, stacked, right? Stacked shifts data, just like that. All right, and that's done. So let's take a look at the summary of the model. Okay, summary of Kruskal test underscore, bam. All right. It doesn't show me much, right? I was hoping that the summary will give me more details. So how about this? We're going to run the same test. That's kind of unexpected. I'm going to run the same test, but without assigning that to anything. Just gonna say, run the test for me. And there it is, okay? I knew that will work, but I was hoping that when I ask for the summary of the Kruskal test, it will be able to provide me the summary. But yeah, apparently it doesn't work that way with Kruskal test. Okay, anyhow, so this is the result of my Kruskal-Wallis rank sum test, or for short it's oftentimes called Kruskal-Wallis test, and that's it. Okay, so it looks like our p-value is 0.78, right? So that's a very large p-value, obviously. P-value is 0.78 0.79 even, right? If I round it up, that's obviously greater than 5%. So what do I do when p-value is high? Fail to reject the null in favor of alternative. And what does my null say? My null says that the distribution of customer ratings for shifts 1, shift 2, and shift 3 are statistically the same. So in other words, that's statistical answer, right? So I have to now translate the statistical answer in terms of the human, right? This is business statistics. So original question was, do I provide the same level of customer service during 3 shifts? Then I collected the ordinal data, and then I translated my business question into that question for the in the statistical language, right? Locations are the same versus not the same, and I ran the test. It gave me the p-value. I failed to reject the null, so therefore my answer, statistical answer, right, is that locations are the same. Now I have to translate that into the human language again, right? What does that mean? That means the distribution of customer ratings for shifts 1, 2, and 3 are statistically the same. So therefore, during the day, I provide consistent customer service. Case closed. Everybody's happy. Okay. So that's that's how we use Kruskal-Wallis test. So again, it's very similar to what we do for one-way ANOVA, but again, one-way ANOVA is limited because it applies only when your samples are independently collected and normal. Okay, when they're not normal, or when the data are not numerical, they're ordinal to begin with. So there is no normality, they're just simply ordinal, like in this case, then we have to use Kruskal-Wallis test. Okay, so that concludes our course, quite frankly, okay? There are a lot of different things that we can discuss, but I believe that the course was had pretty good coverage, okay, as is. So we didn't discuss things like two-way ANOVA and two-way ANOVA with replications. We didn't discuss Friedman test, which is analog of the two-way ANOVA, so matched pairs essentially, okay, or blocks. What else didn't we discuss? We didn't discuss actually Spearman rank correlation test. That might have been useful. But anyway, the tests that we did discuss, they cover the majority of cases on this flow chart. So therefore, that should give you pretty good picture about which test is applicable in which situation. And like I said in the middle of the semester, statistics, this is classic statistics. Okay, so this is science which is probably 200 years old. Okay, not all of that, of course. I mean, it's developing all the time, but this what we discussed, it was in progress, in development, probably in the last 200 years. Okay, so therefore I consider that to be classic statistics, and it's just from the applied standpoint. Okay, it's just a lot of tools, and each tool, each test has its own applicability, right? So each test relates to what are you doing? Are you looking at one population or two or three or more, or is it about relationship between X and Y? What is that, right? And then next question, of course, what kind of data are you dealing with? Are your data numerical or nominal or ordinal, right? And then if it's nominal, if it's numerical, then the question becomes, okay, how are things distributed? Are they normally distributed or are they not normally distributed? Also, they can be collected as matched pairs or independent samples. So all of these different scenarios, what if analysis kind of thing, they come with their own test flavor. So therefore, knowing statistics is really boiling down to the question, do you know, like you have a data set and you have description. What is that you're trying to do and how exactly did you collect the data? So based on that, based on this information, you should be able to pick up the test, and each time when you select the test to apply, you have to be able to use it. In other words, formulate what's your null and what's your alternative, pick the right function from the R or RStudio, run it, get the p-value out of that, do the conclusion, keep the null or reject the null, and from that drive your answer to the original business question. So this course essentially is just a review of a bunch of different tools which are in the toolbox, which is called statistics. Okay, so the attempt in this course is try to make Luther students into the intelligent users of different tools available in the statistical toolset. So this concludes our course. I hope you enjoyed it, and the next stop is the final exam.